Hello everyone, this talk is about improving approximate pure Nash equilibrium and congestion games. This is joint work with Alexander Skopalik from the University of Twente in Netherlands. So the agenda for the talk. So first I would introduce you to congestion games, what a pure Nash equilibrium and congestion game means, or what an approximate pure Nash equilibrium and congestion game is. Then we look at some of the related work, and then I introduce you to our results and the algorithm that we use to get these results, and we look at the correctness of the algorithm. I will not get into the technical details of the proofs, but I just give you a proof idea. And finally, I would conclude with some open problems. So let's get started. So a congestion game basically consists of a set of n players, u1 through un, and there are a bunch of resources, e1 through em. Each of these resources has a non-decreasing latency function or a cost function associated with it, and these cost functions are usually dependent on the number of users on that resource. Every user or every player has a bunch of strategies where each strategy consists of a collection of resources. A state in a game is basically the collection of the strategies used by all the players at any given point in time. The cost of a player, U, in any given state S would then be the sum of all cost of all the resources used by that player. Now remember, the cost of a resource depends on the number of players on that resource. So let's look at an example. So in the graph below, there is a single source and a single destination, and players would like to go from the source to the destination. There are two routes, the top edge and the bottom edge. The top edge has a constant cost of 2. That means any number of players on the top edge, each of these players pay a cost of 2. The bottom edge has a linear cost function, which basically means the cost of a player depends on the number of users on that edge. Now, we should note that in a congestion game, the players in a congestion game are selfish, which means they always pick up strategies that minimize their cost. This brings us to the notion of a Nash equilibrium. So, a best response move for a player from any given state is to pick that strategy that minimizes this player's cost amongst all the other strategies, while all the other players are frozen to their strategy in the state. Now, we say a game is in a pure Nash equilibrium if none of the players have such a best response move. Now, let's look at the previous example and see what a Nash equilibrium is. So, let's just say there are two players. There's a red player and the blue player, and in any given state, and in this particular state, both these players decide to use the top edge. Now, each of these players pay a cost of 2. However, this game is not in an equilibrium since one of these, in fact, both of these players have a best response move. Now, let's just say one of these players decide to pick the best response move. That is, let's say the red player decides to go to the bottom edge. Now, the red player has a cost of 1, and the blue player still has a cost of 2. But this game now is a pure Nash equilibrium because none of these players have a better deviation move. That is, the red player does not want to deviate to the top edge because that would only increase his cost, and the blue player does not want to deviate to the bottom edge because the cost doesn't change. And we say the game is in an equilibrium. So now that we show that this game is an equilibrium, the question that arises is that does every congestion have a pure Nash equilibrium? That is, does a pure Nash equilibrium always exist? So Rosenthal showed that in every congestion game has a pure Nash equilibrium. He showed using a potential argument that every congestion game has a pure Nash equilibrium, and we call this potential function the Rosenthal potential function. So Rosenthal potential function basically maps every state in a game to a non-negative real number. So the potential function is defined as shown here, where n sub e s is the number of players on a resource E in the state S. And then you sum up the staircase sums over all resources. That gives you the potential in the state S. Now the potential function has this really nice cost revealing property that every time a player makes a best response move, or every time a player deviates to a new strategy, the change in cost of this player is exactly equal to the change in potential. Which basically means when players make their best response move, when they unilaterally deviate, they are inadvertently also improving the potential. This implies at the local optima or any of the local optima of the potential function, there is a pure Nash equilibrium. Now, using this argument, one can show that every congestion game has a pure Nash equilibrium. Now that we've shown that every congestion game has a pure Nash equilibrium, the next question would be, can you compute these pure Nash equilibrium efficiently? So can a pure Nash equilibrium be computed efficiently? Unfortunately, that is not the case. So Fabricant, Papadimitriou, and Talva show that in general, it is PLS complete to compute a pure Nash equilibrium and congestion games. That is, there are games and there are states and initial states in the game from where it would take exponential number of moves before the game converges to an equilibrium. They show that it is PLS complete for general congestion games, for symmetric congestion games. So when I say symmetric congestion games, all the players have the same set of strategies, and also in asymmetric network congestion games. In case of symmetric network congestion game, they show that pure Nash equilibrium can be computed in polynomial time. So due to this negative result with respect to the complexity, we look at a different notion of pure Nash equilibrium called the approximate pure Nash equilibrium. So an approximate pure Nash equilibrium is a rather weaker notion of a pure Nash equilibrium, where now instead of a best response move, you have an alpha best response move for some alpha greater than 1, which means a player can only deviate to another strategy only if this deviation gives the player an improvement of at least by a factor of alpha. So a player deviates if the deviation improves the cost or improves the cost of the player by a factor of alpha. And we say a game is an alpha approximate via Nash equilibrium if none of the players in the game have such an alpha best response move. So now that we have a notion of an approximate pure Nash equilibrium, is it possible to compute good constant factor approximate pure Nash equilibrium in polynomial time? So Sheehan and Sinclair show that in symmetric congestion game, if we assume the resources to have a mild condition on their latency function called the beta bounded jump condition, then they show that a sequence of alpha best response move always converges to a alpha approximate pure Nash equilibrium in polynomial time. However, this is not true in general. So Skopalik and Poking show that for any alpha greater than 1, for any polynomial time computable alpha greater than 1, there always exists a congestion game in which computing an alpha approximate pure Nash equilibrium is PLS complete. They show congestion games with arbitrary cost functions that do not have a alpha approximate pure Nash equilibrium that can be computed in polynomial time. Now that brings us to the question, what if we restrict these cost functions in the congestion games to be a certain class of cost functions? So in their construction, they use arbitrarily steep cost functions. But let's just say we restrict these cost functions to a certain class of cost functions. Then can we compute good approximate pure Nash equilibrium in polynomial time? So let's just say we restrict our congestion games to have only polynomial cost functions. Then can we come up with good constant factor approximate pure Nash equilibriums that can be computed efficiently? So Karagiannis, Fanelli, Krabin, and Skopalik in their seminal paper show that for polynomial congestion games, a constant factor approximate pure Nash equilibrium can be computed in polynomial time. Particularly, they show that in case of linear cost functions, you can compute their algorithm computes a 2 plus epsilon approximate equilibrium in polynomial time, and they have similar results for high degree polynomials. So in our paper, we use their algorithm, we adapt their algorithm using a linear programming approach, and we try to improve the constant factor in this constant factor approximate pure Nash equilibrium. So these are our results. We basically significantly improve the results in Karagiannis et al. Using an adaptation to their algorithm using a linear programming approach. Particularly for linear cost functions, we improve from 2 plus epsilon to 1.61 plus epsilon approximate pure Nash equilibrium. For the rest of the talk, we just assume that all the cost functions are affine or linear. We show that for every epsilon greater than 0, our algorithm, which is basically an adaptation to their algorithm, computes a 1.61 plus epsilon approximate equilibrium in polynomial time. Now let's look at the algorithm. So the algorithm is pretty simple. So first we force all of these players to play their best response move. Now we let the players make a best response move, assuming that they are the only players in the game. They assume that no other player takes part in the game. Once all the players have taken such a best response move, we divide the players into blocks. The players in the block B1 are the bunch of players with the highest cost, and the players in block BM are the players with the least cost. Once we've divided these players, the game continues in phases. So in any given phase I, players in the block BI make a 1.61 plus epsilon move or epsilon best response move with respect to the original cost function. Players in the block BI plus 1 make a 1 plus epsilon move with respect to the modified cost function. Now, I've not introduced you to the modified cost functions. So these modified cost functions are basically non-decreasing cost functions that have to satisfy a certain property that I would describe soon. So at the end of the phase I, players in the block Bi are in a 1.61 plus epsilon approximate equilibrium with respect to the original cost function, and players in the block Bi plus 1 are in a 1 plus epsilon approximate equilibrium with respect to the modified cost function. In the next round, in the next phase, that is phase I plus 1, players in the block Bi plus 1 were already in a 1 plus epsilon approximate equilibrium with respect to f prime, now do a 1.61 plus epsilon move with respect to the original cost functions, and players in the block Bi plus 2 make a 1 plus epsilon move with respect to the modified cost function. At the end of the algorithm, that is at the end of phase mi, end of the phase m minus 1, all the players are in a 1.61 plus epsilon approximate equilibrium with respect to the original cost function. Now let's get into what these modified cost functions are. So I told you these modified cost functions have to satisfy a certain property. Now these modified cost functions are given as an input to the algorithm. So we assume the algorithm is given the congestion game and the bunch of modified cost functions. So these modified cost functions have to satisfy a certain property known as the strong smoothness property. So the strong smoothness is basically a generalization of the lambda mu smoother, Timroff-Cardan's lambda mu smoothness, but now for the potential function. So our strong smoothness is basically a stronger version of the regular lambda mu smoothness in the sense that it's not just sufficient if the congestion game is lambda mu smooth with respect to the potential function. We also require that every subgame in this congestion game is also lambda mu smooth, which basically means you pick any subset of players and you freeze the rest of the players, and you only allow for these players, the subset of players, to do their best response. Then if you look at the potential with respect to these subset of players, they also must be lambda mu smooth. So what this property basically says is that exists for linear cost functions, there exists a bunch of modified cost functions such that it's 1.610 smooth in the strong sense. The next lemma is called the subgame lemma, which basically says if you have a game and let S be some state in the game which is a 1 plus epsilon approximate equilibria with respect to the modified cost functions, and S star be some strategy profile, some state which is a potential minimizer, then this lemma says if you pick any subset of players and you compute the potential with respect to these subset of players in this state S, the state S is a 1 plus epsilon approximate equilibrium, and the potential is at most 1.61 plus epsilon times the potential of this subset of players in the state SR. Using this property and the subgame lemma, we can start looking at the correctness of the algorithm. Again, I will not get into the technical details of the proof. I only give you a proof idea. So first, we want to show that the potential at the beginning of a phase is considerably low. Particularly, we show that after the first phase, the potential amongst players who take part in any given phase is significantly low. Now, having low potential also means there's not enough potential to move, which means we do not have many best response possible. So using this lemma, this turns out to be a very important lemma. We can show that in any given phase, the number of best response moves are polynomially bounded. But the thing is, our algorithm uses two different cost functions, the modified cost function and the original cost function. So the game that we have created is not a potential game anymore. But we show that the Rosenthal potential, the way we pick these modified cost functions, because this modified cost function satisfies the certain property, the strong smoothness property, we can show that the Rosenthal potential with respect to the modified cost function acts as an approximate potential function with respect to the original cost function, which basically means every time a player makes a 1.61 plus epsilon move with respect to the original cost function, they also decrease the potential with respect to the modified cost function. Using this property, we can show that in any given phase, there are at most polynomially many number of best response moves, and to show that the algorithm, once the algorithm terminates after polynomially many best response moves. The next thing that we have to show is that every time a player makes a best response by either a 1.61 plus epsilon move or a 1 plus epsilon move in any given phase I, it does not increase the cost of players who took part in the previous phase significantly. So using this property, we can show that at the end of the game, all the players are in a 1.61 plus epsilon approximate equilibrium. So finally, the algorithm converges in a state such that the state computed by the algorithm is a 1.61 plus epsilon approximate Nash equilibrium. So we show that at the end of the game, the end of the algorithm, all the players are in a 1.61 plus epsilon approximate equilibrium, and it only took polynomially many rounds or polynomially many best response move for the game to converge to a 1.61 plus epsilon approximate equilibrium. Now, the key thing to note is that we take this algorithm by Karagianis et al. And we make a minor adaptation to it where we introduce this modified cost functions, which satisfy uh, the strong smoothness condition, and we can significantly improve the approximation factor. The modified cost functions are basically computed using a linear program, where you can give the constraint. One of the constraints of the linear program would be this strong smoothness property, along with the property for that the cost functions are not decreasing. So to conclude, so what we've done in this paper is to show that we can use the algorithm in Karagianis et al. And we can use a linear programming approach to significantly improve the approximation factor that is achieved using this algorithm. That can be done in polynomially many rounds. We also show that we can use a similar approach of constructing or of deriving such modified cost functions to compute optimal load-dependent universal taxes to lower the price of anarchy in congestion games. So let's recall what a price of anarchy is. So price of anarchy is the worst case ratio of social cost at an equilibrium to that of the social cost at the minimizer. We show that the price of anarchy of congestion games using optimum universal taxes is exactly equal to the price of anarchy of selfish scheduling on identical machines. So we are able to improve from, for example, with linear cost functions, we can improve from 2.5 to 2.012. Finally, to look at some of the open problems. So one of the main open problems or the interesting directions is to look at the computational lower bound. So far, we only know about the computational lower bound if the cost functions are not restricted to polynomial cost functions. So if you allow for arbitrary steep cost functions, then Skopalik and Foking, they show that its PL is complete to come out to compute any alpha approximate Nash equilibria for any alpha greater than equal to 1. So it would be an interesting direction to look for the lower bound, the computation lower bound, if you restrict the class of cost functions to be polynomial cost functions. And the next question would be the idea of this perturbation, the idea of perturbing the cost perceived by the user in a game to come up with better approximate Nash equilibrium, what we call the modified cost function. If we can use similar approach for weighted congestion games so that we can compute better approximate Nash equilibrium in case of weighted congestion game, that would be an interesting direction to look at. This brings me to the end of my talk, and I'd like to take some questions now. Thank you.